Hello everyone. Today we are going to cover the theory part 6 of D and F block elements of our NCRT chapter 4. So let's start today's topic, NCRT chapter 4 D and F block elements theory part 6, which is covering, and today we are going to cover the NCRT section 4.5 to 4.5.4. This is disclaimer. The objective: after attending this lecture, you will be able to understand the general characteristics of F block elements and the general horizontal and group trends in them. And also, you will be able to describe the properties of F block elements and give a comparative account of lanthanoids with respect to their electronic configurations, oxidation states, and chemical behavior. So the topics that we have to cover today, according to the NCRT, are: the first is the inner transition elements. That means today we are going to talk about the F block elements. The section 4.5, that is the lanthanoids. Subsection 4.5.1, electronic configurations. Subsection 4.5.2, atomic and ionic sizes. Subsection 4.5.3, oxidation states. Subsection 4.5.4, general characteristics. And then we will conclude with summary. So let's begin with the little introduction to F block elements, the inner transition elements. F block is composed of two distinct series. Okay, why we are saying them as F block elements? Because they are existing in the F block in the periodic table. And they are composed of two distinct series. The first one is lanthanoids, in which 14 elements are coming after lanthanum element. The key point is that lanthanum, symbol La, is typically discussed alongside the lanthanoids due to its strong resemblance. General symbol Ln is often used for the lanthanoids. We have these 14 elements of lanthanoid series, starting with cerium, having atomic number 58, and ending with lutetium, atomic number 71. So cerium, parasodium, and neodymium, and promethium, samarium, europium, gadolinium, terbium, dysprosium, and holmium, erbium, and thulium, and ytterbium, and lutetium. So these are the lanthanoids 14 elements with their respective atomic number. The second series under the F block elements is actinoids. The 14 elements are which comes after the actinium element. The key point is that actinium AC is similarly included in the discussions of the actinoids. The actinoids include from thorium to Lr, that is lawrencium. Okay, so thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, and nobelium, and lawrencium. Okay, so these are the actinoids with their respective atomic number from 90 to 103. Let's see the similarities and the differences within the F block. In the lanthanoids, they exhibit greater similarity to each other compared to the members of typical transition element series. So we have seen the transition element series, the D block elements. So comparing to them, they exhibit similar similarity at a greater extent to each other compared to the member of transition element series. They possess one stable oxidation state. Okay, if you remember, we have seen that in the transition element series they have different oxidation state, but lanthanoids, if you talk about lanthanoid, they possess only one stable oxidation state. Their chemistry offers a valuable opportunity to study the impact of subtle changes in size, in nuclear charge, in these two, changes. So, if you study about the lanthanoids, you can also consider to study about their change in size, a little change in their sizes and the nuclear charge. Next, if you talk about the actinoids, their chemistry is significantly more complex compared to the lanthanoids. And this complexity arises from the two main factors. The first one is the wide range of oxidation states observed in the actinoid elements. Secondly, their radioactivity. So the actinoids are radioactive, which present a unique challenge in their study. So let's start with the section 4.5, the lanthanoids, in which lanthanoid series elements and its mnemonic. So this is the table showing element symbol, element name of lanthanoid series and their mnemonic word. Okay, these are the words which can be used to remember the series. So if you start with cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. So if you want to remember what is coming after what, so you can consider these words like sir, par, nadi, पैरों में समुंदर, अरे गॉड तुम दयालु हो और तुम यहाँ भी लूटोगे. Okay, so like sir, ce, resemblance. Okay, par, that means pr, nadi, that means nd, पैरों में, that means pm, samundar, that means sm, array, that means eu, god, that means gd, tum, that means tb, dayalu, that means dy, ho, ho, or er, tm, tum, yb, यहाँ भी lu, लूटो. Okay, so this is how you can remember the series. Let's talk about the electronic configurations 4.5.1 of the lanthanoids. Atomic electronic configurations. So common feature is that all the lanthanoids atom consistently have 2 electrons in their outermost 6s orbital, that is 6s2. Okay, so if you observe within a series of lanthanoids, all the lanthanoids atom have 2 electrons in their outermost 6s orbital. Every element is having 6s2, 6s2, 6s2. Okay, in their electronic configurations. This stable 6s2 configuration is a defining characteristic across the series because it is present in all the lanthanoid atom across the series. If you see this table, so in this column we have property, and in the series in this row we have different like elements present in the lanthanoid series, starting from lanthanum and ending to lutetium. Okay, their electronic configuration is given according to the lanthanoid series. Okay, you observe 6s2, 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 6s2. Every element have 6s2 configuration. That means it is a characteristic you can define across the series. If you talk about the electronic configuration of lanthanoids 2 positive, then the 6s2 will be gone and only the remaining electron will be here present. And then electronic configuration in the case of lanthanoids 3 positive will also be given. Okay. Variable occupancy of 4f level. Primary difference in their atomic configurations lies in the variable number of electrons which is occupying the 4f subshell. If you observe the electronic configurations among the lanthanoid series, there is a difference in their atomic configurations which lies in the variable number of electron filling in the 4f subshell for every element. As you move across the lanthanoid series with the increasing number of atomic number, the electrons are progressively added to the 4f orbitals. Okay, that means progressively added to the 4f orbital means in the 4f orbital, if you consider, we can fill a maximum of 14 number of electrons. Okay, so if you move across the lanthanoid series, if first element is having 1 electron in the 4f orbital, the another one will have 2, the next one will have 3, the next one will have 4. Okay, so as you move across the lanthanoid series, electrons are progressively added to the 4f orbitals. The important note here is that while the 4f subshell fill, there can be some irregularities involving the 5d orbital. That means still there are cases that 4f subshell fills, there is also some irregularities involving the 5d orbital, that electrons are going into the 5d orbital. Like if you observe, in the case of cerium, the first element, and the lanthanum, they both have 5d1 present in their configuration. Okay, in the cerium, the electronic configuration is xenon 4f1 5d1 6s2. So still the 4f subshell is filling. There is a irregularity involving the 5d orbital where one electron is going. You can observe this in this given table again with the electronic configuration. So cerium is having 4f1 5d1 6s2. Okay, similarly in the GD, that means GD means gadolinium. If you observe, we have 4f7 then 5d1, and similarly in the lutetium we have 4f14 and then 5d1. Okay, so 4f subshell is filling. There is irregularity involving 5d orbital in these elements cases. Now, electronic configurations of tri-positive ions. So let's see the electronic configuration of tri-positive ions. That means lanthanoids having 3 positive charge. So the most stable oxidation state, the tri-positive ion, that is Ln3 positive, is most stable and common oxidation state for all the lanthanoids. Across the lanthanoid series, for every element, their existence in the 3 positive oxidation state is the most stable and the common oxidation state observed along the lanthanoid. The general form, so the general electronic configuration for the lanthanoids is 4Fn 5D0 to 1 6S0 to 2. Okay, N in the 4F can be filled from 1 to 14, and D5D can be filled only from 0 to 1, and 6S can only be filled from 0 to 2. Maximum generally 6S2 is present in every element configuration along the lanthanoids. So this is general configuration for lanthanoids, and the electronic configuration of these tri-positive ions uniformly take the form 4Fn. Okay, so this electronic configuration, when achieved by the lanthanoids, that is lanthanoid having 3 positive charge, the tri-positive ions after attaining 3 positive charge uniformly will going to take the form of electronic configuration 4Fn. The N here is representing the number of electrons present in the 4F subshell. Okay, as you know, the 4F can contain maximum of 17 electrons, and half filled will be 4F7. Okay, the range of N, so value of N will increase from 1 to 14 as the atomic number increases across the series of the lanthanoids. Example, a lanthanoid with the atomic number X will have 4Fx configuration in its +3 ion, where small x is its position in the 4F series. Okay, so this is capital X and this is small x here. So if a lanthanoid having atomic number capital X will going to have this 4Fx configuration in the +3 ion, that means when this lanthanoid X will become tri-positive ion, that means when it will going to attain +3 charge, it will going to have 4Fx configuration, where the small x in the 4Fx configuration is the position in the 4F series. Okay, so key takeaway here is that in the Ln3 positive state, in the tri-positive state of the lanthanoids, the 6s2 electrons and any initial 5d electrons, if present in the atom, are removed, leaving only the electrons in the shielded 4F subshell. So the point to remember, or a key takeaway from here, is that if you have a tri-positive ion of lanthanoid series, then the 6s2 electron of that element and any initial 5d electron if present in that atom are removed already, and only leaving that tripositive ion, the electrons of it into the shielded 4f subshell. Okay, because if you see this, observe the electronic configuration. If you have +3 charge on the lanthanoid, that means this 2 electron have been removed from here. 1 electron from the 5d have been removed from here if present in the atom. If not, then 1 electron will go from this 4f. But still in the +3 state, the ion will going to have this configuration of 4f(x), okay, where x is showing the position of it in the 4f series. Let's move to our next subsection, 4.5.2, that is atomic and ionic sizes. So let's talk about the lanthanoid atomic and ionic sizes. One of the most distinctive and significant feature of lanthanoid chemistry is the trend in their atomic and the ionic sizes. Okay, so if atomic means when they don't have any charge, ionic means when they have some charge like +3. So the important and the distinctive feature of lanthanoid chemistry is the trend observed in their atomic and ionic size. Lanthanoid contraction, which is a unique feature. Okay, lanthanoid contraction, you have heard about it. So there is an overall decrease in both atomic and ionic size or ionic radii as you move from lanthanum, that is La, to lutetium, that is Lu, across the lanthanoid series. So if you move across the lanthanoid series, there is a overall decrease in the atomic and the ionic radii. Okay, so from the lanthanum at the very starting of the lanthanoid series to lutetium at the very end of the lanthanoid series, there is a observance of decrease in atomic and ionic radii. This consistent decrease in the size is known as lanthanoid contraction, and this decrease we are talking about is having a name, that is lanthanoid contraction. Okay, so lanthanoid contraction is basically occur due to the poor shielding effect shown by the 4f electron to protect the outermost electrons from the increasing nuclear charge. So it has poor shielding effect, so those outermost electrons is going to affect by the increasing nuclear charge, due to which the atomic size is going to be decreased. The highlight, this contraction, lanthanoid contraction, is a unique and defining characteristic in the chemistry of lanthanoids. What are the consequences of lanthanoid contraction on third transition series? So the lanthanoid contraction has a far-reaching consequences. That means from the F or F block elements, we are talking about third transition series. Okay, like 3D, 4D, 5D. So 5D series we are talking about, that the lanthanoid contraction has far-reaching consequence for the chemistry of elements in third transition series, where the elements like hafnium and tungsten that follow the lanthanoids in the periodic table are present, right? So lanthanoid contraction is also going to affect them, the third transition element, the third transition series elements. Radii of lanthanum and lanthanoids. So this is the table showing the atomic number, the element name, its symbol, its radii in the picometers in the lanthanum form, and the radii in picometer in the like tripositive ion, lanthanium 3 positive. Okay, so if you see, atomic number is 57 for lanthanum, symbol La, radii is having 187, but Ln in 3 positive will having the radii of 106. If you observe across the series, the radii is decreasing. Okay, and here also the Ln 3 positive radii is decreasing. Okay, somewhere you can see the like exception where this 180 and it is coming to europium and it is becoming 199. The radii is becoming 199. It is you can relate it to the configuration of this, because it is attaining the half-filled configuration by attaining 4f7 electrons. Okay, that's why the radii will be 199, the larger one for the europium. Okay, then it is decreasing and and then it is decreasing. Okay, so this is how the radii for the lanthanum and the lanthanoids are given across the series. Now the trends in the radii. First of all is the atomic radii of metal. So let's see the trend in them. While there is a general decrease, the decrease in the atomic radii is not perfectly regular. Okay, so if you observe, there is a general decrease in the atomic radii of the lanthanoid series elements, but the decrease in the atomic radii is not perfectly regular. So ionic radii, if you talk about, of M3 positive ions, then in contrast to the atomic radii, the decrease in the radii of ions M3 positive is quite regular and consistent. Okay, if you compare with the decreasing radii trend between the atomic radii of metal and ionic radii M3 positive ions, then you observe that the decrease in the radii of M3 positive ions is quite regular and consistent compared to the atomic radii of metals. The highlight point is here that this regular decrease in the ionic radii in the form of M3 positive ions is a crucial observation. Okay, so decrease in the ionic size is a crucial observation. You can see here in this diagram representing the trend in ionic radii of the lanthanoid series. So how with the atomic number increase, the ionic radii in the picometer is decreasing. It is showing, right? So lanthanum, so this line, dotted line, okay, like these dots are representing each element in the 3 positive state in the ionic form, okay, and these dots are connecting. So you can see there is a general decrease in the ionic radii of the lanthanoids in the 3 positive state from lanthanium to lutetium. Meanwhile, there are some, other points which are mentioned here, like for here SM, that is samarium and europium in the 2 positive state. Okay, so europium in the 2 positive will attain 4f7 configuration, and the samarium is just element before the europium. So they can both exist in the +2 state also. So in the +2 state, how the ionic radii will change with the atomic radii, that is shown by this. Similarly, in the TM, that is thulium, and YB, that is ytterbium, they are in +2 oxidation state. That means if you talk about ytterbium, it is after releasing 2 electrons from the 6s2, it will going to have 4f14, like fulfilled f orbital, which is going to be stable, and they both are existing in +2 oxidation state. And how their +2 oxidation state ionic size is going to be changed with the atomic number, this is represented by this. And here Ce and Pr, Ce is cerium and Pr is paraceriodium, paraceriodimium. So they both are in 4 positive state, because if you see cerium in the 4 positive means it will lose its all the outermost electrons and attain a noble gas configuration, and this paraceriodimium is just a element after cerium. Okay, so how they both can be present in the +4 oxidation state. So how they the ionic radii of them in the ionic form will change with the atomic number, this is shown by this. And here the Tb in the +4, Tb means terbium in the +4, plus terbium in the +4 means it will lose its 6s2 2 electrons, and 4f9, from 4f9 2 electrons, so 4f7 it is going to attain half filled. So how its ionic size will lie somewhere here as per its atomic number. Okay, so this is the trend showing a general decrease in the size of ionic ions, okay, in the M3 positive form, which is regular and consistent. You can observe that by this regular line. Cause of the contraction: imperfect shielding. So the contraction in the size is fundamentally similar to decrease in the size observed across an ordinary transition series. Okay, so what is this contraction cause? Why the size is decreasing if you move across the lanthanoid series? Okay, maybe due to imperfect shielding, right? As I said, due to the 4 of orbitals showing the poor shielding, providing the poor shielding. And this contraction is fundamentally similar to decrease in size which we have observed across the ordinary transition series. Underlying cause is imperfect shielding of one electron by the another in the same subshell. The key difference for lanthanoid is that, however, shielding provided by one 4f electron for another is less effective than the shielding provided by one d electron for another, and even as the nuclear charge increases along the series. That's the difference between the lanthanoids and the transition series, if you talk about the decrease in the size. Okay, so imperfect shielding of one electron by the another one in the same subshell is the cause for the increase or for the decrease in the size which you have observed in the transition series. And the difference from the lanthanoid is that the shielding provided by one 4f electron for another is less effective than the shielding provided by one d electron for another, even the nuclear charge increasing along the series. This very poor shielding shown by the 4f electron is primary reason for the significant contraction along the lanthanoid series. And the overall trend is that due to this there is a fairly regular decrease in the sizes, especially the ionic sizes, with the increasing atomic number. So overall trend is that the ionic size will decrease with the increase of atomic number. Cumulative effect, that is the impact on the third transition series. So the cumulative effect of contraction throughout the entire lanthanoid series is profound. The result is that it causes the radii of member of third transition series, that is 5d, to be very similar to those of their corresponding members in second transition series, that is 4d. Okay, so this effect of contraction causes the radii of member of 5d series and the 4d series very similar. For example, almost identical radii of zirconium having the radius 160 picometer and hafnium having the radius of 159 picometer are a direct consequence of lanthanoid contraction. So why, if you observe between the 5d element zirconium and the 4d element hafnium, okay, they both are having identical radii due to this direct consequence of lanthanoid contraction. What are the practical implications? So this similarity in size explains that why the zirconium and hafnium often occur together in the nature and why their separation is remarkably difficult in the industrial process. If you want to use somewhere zirconium and some at other places hafnium, why it is very difficult to separate these two in the industrial process and why in the nature they exist both together. These things are explained by their similarity in the sizes. So if you observe, this was the graph we have seen for the trend in the atomic radii of transition element for the different series, like 3d series the green one, 4d series the blue one, and 5d series the red one. If you observe, the red one and the blue one are very close. That means their sizes, their atomic sizes or atomic radii are very close to each other. Zirconium lie here in the 4d series and the hafnium lie here in the 5d series, same, right? So their radii are almost identical. And there is a very large gap between the 3d series radii and the 4d series radii. Okay, and this is the like ionic size like observation for the lanthanoids. Okay, so due to this lanthanoid contraction, or this lanthanoid contraction is also going to affect the radii or the members of the third transition series to be very similar to become to the second transition series, that is 4d and 5d. Due to this contraction this happens. Okay. Let's talk about the oxidation states 4.5.3 for the lanthanoids. So, the predominant oxidation states, the most common and significant oxidation states for the lanthanoids are lanthanum 3 positive and the Ln 3 positive compounds. Okay, so lanthanum exists in plus 3 and Ln, that is lanthanoids, are existent plus 3 compounds, which is the most common and the significant oxidation state found in lanthanoids. So what does that mean? It means that for lanthanum, plus 3 oxidation state is dominant, and for all the other lanthanoids, plus 3 state is also most prevalent. The occurrence of other oxidation states. So if you see the other oxidation state we have observed in the graph, right? For someone the plus 2 and for some the plus 4, depending upon their stability. So occasionally plus 2 and plus 4 ions can also be observed. These can exist either in the solution or within the solid compounds. Why is the reason for this irregularity in the oxidation state? This irregularity in the oxidation state is primarily attributed to extra stability gained from having empty, that is F0, half filled, that is F7, or completely filled, that is F14, F subshell. So why they show plus 2 plus 4? Because either they are attaining noble gas configuration by having empty F orbital, either they are having half filled orbital F7, or they are having completely filled F14, F subshell. Okay, and due to this excess stability, they show this irregularity in the oxidation state. So from plus 3, they will also show plus 2 and plus 4. Specific examples of plus 4 oxidation state. So let's talk about this plus 4 oxidation state shown by the lanthanoids. The first is the cerium. Cerium will show plus 4 oxidation state. So the formation of cerium 4 positive, where cerium is having plus 4 oxidation state, is favored. Why? Because it is going to achieve a noble gas configuration by having empty F orbital, that is F0 it is going to have, and it is going to attain a noble gas configuration which is going to be stable. Important property that however the cerium 4 positive is a strong oxidant, this means it readily gains electrons to revert back to its more common and stable plus 3 oxidation state. Okay, however we have this, that cerium 4 positive is a strong oxidant. This is going to gain, or it readily gain electron to revert back to its more common oxidation state and the stable one, that is plus 3. The redox potential. So standard electrode potential for cerium 4 positive to cerium 3 positive couple is positive 1.74 volt. Okay, so it has a positive value for the cerium 4 positive to cerium 3 positive of its standard electrode potential, and this high positive value suggests that cerium 4 positive has a potential to oxidize water and reduce itself. What is the practical use now? Despite its strong oxidizing potential, the reaction rate with the water is very slow, and this makes the cerium 4 positive a good analytical reagent in the titrations process, as its reactivity is under controlled. Okay. The other elements which exhibit plus 4 state are praseodymium, that is Pr, neodymium, terbium, dysprosium. They also exhibit plus 4 oxidation state. Now what is the limitation? So however these elements, for these elements plus 4 state is observed only in their oxides, specifically as MO2, where M is the lanthanoids. Okay, so these elements show plus 4 state in their oxides, which are specifically in the form of MO2, where M is representing a lanthanoid. Now let's talk about specific example of plus 2 oxidation state, the elements going to show plus 2 oxidation state in the lanthanoids. So first is europium, that is Eu2 positive. The formation of Eu2 positive is when the europium loses its 2,6s electron, because 6s2 is present in every element, right? So 2 plus means it is going to lose its 2 electrons from 6s and going to attain the 4f7. Okay, so if we talk about stability, its formation is accounted for EU2 positive, its formation is accounted by its resulting F7 electronic configuration, which is half filled F subshell, which provides it a extra stability. What is the important property? That despite the stability of half filled F subshell, europium 2 positive is a strong reducing agent. This means it readily loses an electron to transform into the more common stable oxidation state, that is +3. Next example showing +2 oxidation state is ytterbium, Yb2 positive. Similarly, Yb2 positive also exhibit +2 oxidation state due to the similar reason, the stability, that is due to its F14 electronic configuration, which is completely filled F subshell and which imparts extra stability, which provide extra stability to the Yb2 positive ion. The important property that like europium, the Yb2 positive ytterbium is also a reductant and tending to get oxidized to +3 state, which is a common and stable oxidation state observed in the lanthanoids. Another example is samarium. Samarium behaves very similarly to europium and it exhibits both +2 and +3 oxidation state. +2 by losing its 6s2 electrons, +3 because it is a common and stable oxidation state shown by lanthanoid. So it is going to anyway present in +3 oxidation state. Specific example showing +4 as an oxidant. Okay, so specific example of +4 as an oxidant. So first is terbium, that means Tb in +4 oxidation state. Terbium in +4 possesses half-filled f orbital configuration. And despite this F7 stability, terbium +4 act as an oxidant and suggesting tendency to revert to +3 state, the common oxidation state. Now let's talk about the general characteristics 4.5.4, in which we first talk about the physical appearance and hardness. All the lanthanoids are silvery white, soft metals. They tarnish rapidly in air, indicating their high reactivity. Their hardness generally increases with the increase of atomic number. Samarium is notably hard, comparable to the steel. Now, if you talk about the metallic points and metallic properties, their melting points typically range between 1000 Kelvin to 1200 Kelvin. Samarium is an exception here with a higher melting point than this range. It is of 1623 Kelvin. They possess a typical metallic structure. They are good conductors of heat and electricity. Density and the other physical properties change smoothly, with some exceptions for europium and ytterbium, and occasionally for samarium and thulium. So these are the physical properties of the lanthanoids. Let's talk about their color shown by them and the paramagnetism. So many trivalent lanthanoid ion, that means in the +3 oxidation state, they are colored both in the solid compounds and in the aqueous solutions. The color is primarily attributed to the presence of F electrons and La3+, that is lanthanum 3+, having F0 configuration, and Lu, lutetium 3+, having F14 configuration. So these ions do not show any color, but all the other trivalent lanthanide ions do. Absorption bands for their colors are narrow for these two ions, likely due to the excitations which is occurring within the shielded F level. The paramagnetism. So lanthanoid ions that are not of F0 type, like lanthanum 3 positive and cerium 4 positive, and not the F14 type like Yb2 positive and lutetium 3 positive, are all paramagnetic due to the presence of unpaired F electrons in them. So paramagnetism, that means there is an unpaired electron present in the element. Next, let's talk about ionization enthalpies. The first ionization enthalpy of lanthanoids are around 600 kilojoule per mole. The second ionization enthalpy are about 1200 kilojoule per mole. So the first ionization enthalpy to remove the first electron, second ionization enthalpy to remove the second electron is much higher. These values are comparable to those of calcium. And the third ionization enthalpy is a detailed examination of variation in the third ionization enthalpy suggests that exchange enthalpy considerations similar to those in the 3d orbitals contribute to the stability of empty, half-filled and completely filled F levels. Okay, so if we have been examined the variation in the third ionization enthalpies in the lanthanoid series, which suggests us that the exchange enthalpy considerations contribute to stability of empty, half-filled or completely filled F levels. The stability is evident from the abnormally low values of third ionization enthalpy for lanthanum, gadolinium and lutetium. For these three elements, the third ionization enthalpy is very low, because if you see the you can see that, or you can check that with their electronic configurations. Okay, for lutetium it is going to the third ionization enthalpy means the one electron is going to remove from 5d1. In the lanthanum, third electron is going to remove from 5d1. In the gadolinium, third electron is removed from 5d1. Okay, so the stability of this is evident from the abnormally low value of third ionization enthalpy, because they are going to attain stability after removing their 5d and 6s electrons. They are going to attain either 4f7 or 4f14 or the noble gas configuration in the case of lanthanum. Okay, so that's why their values of third ionization enthalpy is going to be lower. Their chemical behavior and reactivity. So the earlier members of series are quite reactive, similar to calcium. However, with increase of atomic number, they behave more like aluminium. The standard electrode potentials, that is E0. So for half reaction, Ln, that is lanthanoids in the 3 positive state, gain 3 electrons, become lanthanoid in the solid form. And the E0 value, the electrode potential value, are in the range of -2.2 to -2.4 for this half reaction. The exception is for europium, whose value of electrode potential is -2.0 volt. And this indicates a small variation in their reducing power, right? So E0 tells us about the reducing power of the element. Now, the reaction of lanthanoids with non-metals. So combining with the hydrogen, when gently heated, they form carbides like Ln3C, Ln2C3 and Lnc2 types. When they heated with carbon, they liberate hydrogen from dilute acids. When they react with dilute acids, they liberate hydrogen. They also burn in halogens to form the halides. And if you talk about the oxides and hydroxides of lanthanoids, they form oxides of the general formula M2O3. They form hydroxides of MOH3 type. These hydroxides are definite compounds, not merely hydrated hydroxides. Okay, and their hydroxides are basic in nature, similar to the alkaline earth metal oxides and the hydroxides, the group 2 metal oxides. So this is lanthanoids. This can show various chemical reactions. So it can even burn in oxygen form oxide. It can even it can even liberate hydrogen after reaction with acid. It can react with halogen to form halide. It can react with water to form hydroxide. It can react with water at particular temperature to form carbides. It can even heat with the nitrogen to form nitrides, and it can heat with sulfur to form sulfides for the lanthanoids. Okay, so this image is showing various chemical reactions shown by the lanthanoids. Applications of lanthanoids. So the best single use in the production of alloy steels for plates and pipes. Mish metal, a well-known alloy which consists of a lanthanoid metal about 95% and iron which is about 5% with the traces of sulfur, carbon, calcium, aluminium. A significant amount of mish metal is used in magnesium based alloys for making the bullets, shells, and lighter flints. Catalysis or catalysis. Mixed oxides of lanthanoids are employed as catalyst in the petroleum cracking process. Phosphors. So some individual lanthanoid oxides are used as phosphors in the television screens and similar fluorescing surfaces. So these are the applications where we can use the lanthanoids in various ways or in various industries or fields. Okay, so let's cover the summary. We have covered today the NCERT section 4.5 to 4.5.4. So we have talked about the F block, in which lanthanoids we have jumped into that after the lanthanum similar and one state, and actinoids where after actinium there is complex property shown by the elements, and there is varied states they have shown in their oxidation state, and they are radioactive. Okay, the key point is that lanthanoids are simpler and actinoids are more complex. And lanthanoids, if you talk about, so we have seen their names and symbols from lanthanum to lutetium. There we have seen the electronic configuration, which is mostly 4Fn6s2 and 4Fn for most stable lanthanoid 3 positive positive ions. The exceptions includes lanthanum and cerium and gadolinium and lutetium due to their electronic configurations. The stable ionic forms also some Ln2 positive due to F7, F14 like EU, that means europium, and YB, that means ytterbium, and Ln4 positive are the ionic form that is shown by the lanthanoids due to their stability as per their electronic configurations. F0, F7 like cerium 4 positive and TB means terbium 4 positive. So they show Ln4 positive like Ce4 positive and Tb4 positive, a stable ion. The atomic radii we have talked about, which is generally decrease with the exceptions of europium, because europium is having larger atomic radii. If you talk about ionic radii, it is consistently decreasing due to the lanthanoid contraction, and this contraction or this decrease in the ionic radii is having this name called lanthanoid contraction due to the poor shielding effect shown by the 4F electrons. Electronic configuration of lanthanoids. So we have seen the atomic lanthanoid configuration. They are always having 6s2 in their every element, and they have variable 4F electrons with some 5D irregularities. Ln3 positive ion configuration, which is most stable, and 3 positive is the oxidation state commonly shown by the lanthanoids. So Ln3 positive have always 4Fn or configuration, where n is from 1 to 14. 6s2 and 5D electrons are removed when they form tripositive ion. Lanthanoid contraction we have seen, which is a defining feature, and it says that overall decrease in atomic and ionic radii from lanthanum to lutetium. The cause is due to the poor shielding by 4F electrons, which is less effective than D electrons as their nuclear charge increases. The result is the tripositive ion formation, and they also show regular decrease in ionic size. The major consequence that third transition series elements have similar radii to second series, like example includes zirconium and hafnium. They are almost identical, making them hard to separate, and they exist common or they exist together in nature due to this. We have then talked about lanthanoid oxidation states. The predominant one is +3, lanthanum and lanthanoid. The other states shown by the lanthanoids are +2 and +4, which is occasional depending upon their stability of configuration due to F0, F7 and F14 configuration. The +4 examples are cerium 4 positive having F0 configuration, which is a strong oxidant, good analytical reagent, and it shows slow reaction with water. Other are PR. PR means pseudomium. ND means neodymium. TB means terbium, and DY means dysprosium. They also show +4 only in the oxides of MO2 type. The +2 example where lanthanoid exists in +2 stable state include the europium 2 positive having F7 half-filled configuration. It is a strong reductant. YB ytterbium having F14 configuration, and it is also going to be a reductant. SM, that is samarium, it also exhibit +2 and +3 both oxidation state. Lastly, TB, that is terbium in the +4 having F7 half-filled stable configuration, and it is going to act as an oxidant. And they all are going to convert in the end to the +3, the common and stable oxidation state shown by the lanthanoids. Then we have seen the general characteristics of lanthanoids. The physical characteristic that they are silvery white, soft metals, they tarnish in air. The hardness of them increases, and this SM, that is samarium, which is steel hard. The melting point is ranging from 1000 to 1200 Kelvin. Exception is this samarium having 1623 Kelvin melting point. They are good conductors of heat and electricity. The color and magnetism, so many tripositive ions of lanthanoids are colored due to the F electron present in them, except F0 or F14. Most are paramagnetic, so they like lanthanoids mostly are paramagnetic due to the presence of unpaired F electrons. Ionization, so first ionization value of lanthanoids is 600 kilojoule per mole, and the second one is 1200 kilojoule per mole, the twice. And the third ionization enthalpy is lower for lanthanum, GD, gadolinium, Lu, lutetium, due to their stability of F0, F7 and F14 respective configurations. Because it is empty, it will going to attain noble gas. F7 is half filled, F14 is full filled. Reactivity, if you talk about earlier members like calcium and later like aluminium, so they will react like calcium, the earlier members, and the later member will react like aluminium. And the E0 standard potential value is ranges between -2.2 to -2.4 volt, and they react with hydrogen, carbon, dilute acids and halogens to form halides and to liberate hydrogen in the case of dilute acids, and they form hydrides and carbides also. They form basic M2O3 and MOH whole thrice hydroxide and oxides. And their uses, we have seen that they mainly used in alloy steels, for example metal in bullets and flints, and petroleum catalyst, they are used as petroleum catalyst, and in TV phosphors. Okay, so thank you so much. That's all for today's chemistry session. Thank you.